Hey folks, my name is Yohan Lasorsa and I'm a principal developer advocate in the data team at Microsoft. Welcome to this session where we'll talk about RAG pipelines optimization, among other things. Let's talk about agents. There are many potential agents that you may be building for your applications, and most of those agents need the ability to find relevant information to complete their task. For example, let's consider the agent used by Conf Burgers, a fictional restaurant. We have customers that talk to the agent when they want to buy something or consult the status of their order, and that agent needs to find products or specific order, most likely from a database, which in our case is Cosmos DB. The data types that agent can search for can be diverse, relational, unstructured, audio, images, video, and others. For this session today, we'll specifically focus on structured and text data that may come from a database or documents. In an agentic scenario like this, it means that the agent first has to decide what tools to use for a given request to get the contextual information, and for each tool, we have to provide the best way to search for the information that we need. So let's do a quick demo of our agent that we built for this use case. So here we have our web application for the agent. Let's, for example, ask what's your best spicy burger? So you can see that the agent is thinking, retrieving some information in there. Let's just wait a bit for the result. So we got our answer in there. So yeah, this looks like a good spicy option. But what's more interesting is how it came to that result. So let's have a quick look in there to see. Yeah, we see that there are a few intermediate steps that the agent used to get to that answer. First, it got the list of burgers by calling a tool, then the list of toppings. Many agents use the retrieve information to do RAG, retrieval augmented generation, in which the agent sends the information to the LLM to answer a question. So RAG was one of the first practical use cases for LLMs, and it's still just as relevant today in the era of agents. In this example RAG flow, the user asks about the best spicy burger on the menu. So what we did, we go get the burger option in our database, and those results are sent to an LLM along with the original user question. And then the LLM answers the question, citing the relevant results. So RAG is a way to ground your agent's answers in a context, in our case, the Conf Burger restaurant, and it's often paired with complex search pipelines, but sometimes it doesn't need to be. Back to our user query for spicy burgers, so it's a restaurant and the menu is limited. In fact, there's only 10 burgers, so we don't need a search engine for that. We just call the web API to fetch all the burgers on the menu and we feed it directly to the LLM. So that's basically mostly what we did, except instead of just having the LLM call the API, we used an MCP server to act as the middleman. So this works because the data size in there is very well delimited and small. We only have 10 burgers on the menu, so it can work because it fits in the LLM context with ease and without using much tokens. So no brainer here, we don't need like anything more complex. But now our restaurant has recently made a partnership with Conf World Beers, and we want to be able to recommend beers if the user asks for it. So for example, we have this other user that wants white beer to go with his spicy burger. But this time, the catalog is more than 1,000 beers. So we need a good search pipeline, and what we want is only send the relevant result to the LLM. So sure, maybe some of you may say that nowadays we have LLMs that can fit like million tokens also in their context window, so it may still fit in this specific case the whole catalog inside the context. But even if it fits, you would have an increased latency and huge cost to the large amount of tokens. So it's really not efficient, and most importantly, it doesn't scale. If instead of 1,000 beer, we would have like 10,000 or 100,000, it wouldn't work at all anyway. So when users ask things to agents, there's a huge diversity in their request. We have some queries that are short, some that are long, some are general, some are very specific, some are in the language of the data, and some are in different language, the native language of the speaker. So for example, these are 4 requests that users could make to the Contenso Burgers agent when asking for beer recommendation to go with their menu. So the first user that we have just want French beer, but a very precise alcohol by volume degree. The second user wants a beer with no alcohol, but that pairs well with a spicy food. The third user asks something more vague and taste-oriented. And the final user asks for exactly the same thing, but this time in French. We want our agent to find great results for all of those queries. So there are 2 main search strategies that you've probably heard. Keyword search, which has existed for a while now, and vector search, which got really big in the last few years thanks to better embedding models. Some of the queries by user can be handled better by keyword search, while many will be handled better by vector search. So the real question is, which strategy do we use? And we should actually use both strategies. The optimal search strategy is a full hybrid search stack where we first do parallel vector and keyword searches, then merge the results together, and finally apply a re-ranking step to ensure the best results are at the top. So let's have a look at each of these steps in this stack to understand fully how it works and why it's an important part of an optimal search strategy. Let's start with keyword search, so the good old classic keyword search. The idea here is that we search for the terms in the query and find the results have those terms in the highest frequency. So the best algorithm for that is BM25, a probabilistic ranking algorithm that takes into account the relative frequency of a term proportional to the length of a document. So said otherwise, if the user searches for light, and the document says light all over the place, and other documents don't, then that's probably a good result. So let's try keyword search in our actual database. Let's move on to the demo in there. First, let's have a look at what we have in our database. So here I'm using the Cosmos DB extension. So you can see the 4 databases that we have. Let's have a look specifically at the beer database, and let's have a look at just a random item so you can see what's in the beer's data. So you have the name, the ID, the style, the brewery, the country, the alcohol by volume, description, and flavors and pairing notes. So this is basically all the beers that we have here in our database. You may also have noticed that we have dedicated containers named beer vector. So we'll also have a quick look in there. Let's take this one, for example. So you can see that we have the actual vector data, all the numbers that represents the embedding of the item. This one actually related that's stored in the other container. And we have basically the text that was used to generate the embedding. So it's just taking all the structured data and put in text form. So going back to testing our keyword search. So here I'm using this query, for example, to test, to search for, let's say, a 5% beer from France, and we'll see how it goes against our database. So you can see the SQL query in there, and we're using the full text score function to basically rank our results. So let's just run it. So let's take a look at the results. So we wanted 5% beer from France, and the first result is actually pretty good. France, almost 5%. Second one, same thing. So yeah, top results looks good in there. Keyword search did its job. But yeah, if we look below the two first results, yeah, we have beer from Japan, Netherlands, and Japan. So yeah, after that, and this one, yeah, it's 0% alcohol by volume, so not a great result in there. So yeah, keyword search worked quite okay for the two top results, but not great otherwise. Let's try another request. So this time, searching from something with no alcohol that pairs with spicy food for my pregnant wife. And yeah, this time, results are not so great using keyword search. For example, if we look just as the main request, something with no alcohol, we can see that pretty much all the results have some alcohol in there. So yeah, probably that in that case, because we didn't have the right keyword, so we didn't get any relevant results that match what we initially wanted. So that's why keyword search is a bit hit and miss when it comes to like broader queries like this one. Let's try another one. We want something just light and citrusy. So yeah, first result is quite light, no alcohol. Let's look at the flavor notes. Yeah, clean citrus finish. So yeah, could be considered a good result. Second one, less light, but still okay. Let's look, yeah, gentle citrusy finish. So again, quite good results. Yeah, generally, if we look at the order, it's not so bad, except maybe like the last one, not so light. And yeah, not so much lemon in there too. So let's finally try our final one, which is basically the same light citrusy beer request, but expressed in French. And yeah, this time, not so much light beer, and basically the results are pretty much all irrelevant because our data is stored in English. Making a request in French means that we don't have like the right keywords. So that's definitely something to consider if you want your agents to be able to handle queries in multiple language. You need to consider that when you're deciding on which search strategy to use for your application. So that's why developers were so excited when vector search came out, since it can handle many of the queries that keyword search struggles with. So this time, we're using an embedding model like the Azure OpenAI text embedding free models to create vectors from our content. So when a user query comes in, we embed that using the same embedding model and use the vector similarity metric to find the vectors closest to that query vector. And to make that vector search efficient across millions of vectors, we can use like an approximation algorithm like HNSW or disk ANN. So let's try a vector search with our beer database. Again, just switching from a different script. So you can see we have basically the same setup as before, except this time we are making a vector search. Oh yeah, we have a first step transforming using the OpenAI text embedding free model, transforming the user query into a vector, and then using that vector to basically compute the vector's distance, comparing and picking up the top 5 results. So let's try again with our different queries. So first one, 5% beer from France. And yeah, not so great with that one. The keyword search actually handled it better because like the first two results were from Belgium, so not exactly France, even if they speak French there. 6% is not 5%. This one is a bit closest. And our first actual good result is in third place. And yeah, after that, it's not so bad. But the two top results, not great for that one. Keyword search, not that better. But let's try the one that keyword search didn't handle very well, like the alcohol-free request query. So yeah, this time, at least the top result is 0%. And if we take a look, like all the results are non-alcoholic beers. So one, at least what we wanted was respected in there. So does it pair well with something spicy? See, smoked salmon, maybe not the best one. Second one is better. Spicy food, yeah, tacos. So yeah, at least it's all better results than what we got and more closer to the intent of the request compared to what we got with keyword search. So let's try the third one. That's more general request. So I wanted something light and citrusy. So first result, two top results, not so light. Citrusy, yeah. Grapefruit, orange, so yeah, can be similar to citrus taste. Same for the second one. Third one, yeah, quite light since it's alcohol-free with, okay, something lemon, so citrusy taste. Something light also for the two last results, and tangerine, grapefruit, juicy finish. So yeah, two top results again, not the best one, but that's because when you're doing vector search, results can be a bit noisy, and sometimes, yeah, you get mixed results with some good results and some not so great. So let's try the last one that didn't work at all using our keyword search. So light citrusy beer, but in French. And this time, yeah, it's looking good. First result is actually better, like light, fresh lemon. Yeah, okay, can be light, subtle lemon peel leaves. So yeah, good result. This time it matched what we wanted, despite our request being in French and our data being in English. So it worked better in that case. But yeah, you've seen that for some requests, like the 5% one, it doesn't work so well because vector embeddings don't distinguish well between specific numbers or specific brand names. It's the kind of thing that keyword search is great at. Vector search is better to focus on the concepts, like closing, like in the semantic matches, like, okay, alcohol-free, it's the same as booze-free. Citrusy is basically something a bit bitter and acid. So any fruit that match this taste might be matched using vector search. That's why we should always use both keyword search and vector search. And then we need to find a meaningful way to merge the result. So the most popular algorithm for result merging is called RRF, reciprocal rank fusion. So it sounds fancy, but it's really just a formula that computes a score for each result based off its relative rank in each result set. So that way, if a result show up high in both results, it will be ranked highly in the final merge results. So if a result is high on one but low on the other, it will end up more like in the middle. So let's go back to our database searching using RRF. Okay, so the setup is pretty similar as before. You can see that we have in our SQL query, we are saying that we want the result order by rank RRF. So this is native Cosmos. We're using mixing the full text score, so the keyword search and the vector search in there. We're also doing the two separate requests to get the individual rankings, just to get an idea on why we got this particular score at the end. So let's first try this more broad request, the one for the light citrusy beer. First result, okay, somewhat light beer. Let's have a look. Gentle citrusy finish, so good result. You can see that it was ranked 2 in the keyword search and 14 on the vector search. Let's have a look at the second one. It's actually one that was better ranked on the vector search and a bit less on keyword search. So light because no alcohol and lime zest. So yeah, still good light and citrusy beer. Let's have a look at other results. So all light results. So the one that were from the keyword search were basically not there this time. Lime, orange zest, again, switch orange peel. So basically all kind of good results mixing because the search worked quite okay for both keyword and vector search. Let's try a more difficult request that was working well for vector search, but not so well for keyword search. The one requesting no alcoholic for spicy food. So the first result, as you can see, is quite in the middle for both keyword and vector search. And yeah, it's still a non-alcoholic beer, even though it's not fully 0%. And let's look at the pairings. So pairs well with couscous. So yeah, couscous is quite spicy. So first result is quite good. But if we look at the other results, we still don't have good, at least what we wanted regarding non-alcoholic beer. And yeah, that's because in the end, RRF isn't the perfect solution either, because both vector search and keyword search can yield sometimes noisy results like this, especially keyword search in this particular case. So yeah, if you have average results in both search, you can still surface the best result at the top with hybrid search. So it works relatively well in most use cases, but still isn't perfect as you can see in there, especially with more complex case. That brings us to the final step, re-ranking. We take the merged results and send them through a re-ranking model, whose job is to look at each result, look at the user query, and give a score indicating how well a result matches the query. So we typically use a special kind of model for this called a cross-encoder model, but LLMs can also be used with the right system prompt. A cross-encoder model is the best option since it's actually been trained for this specific task based off human scoring search results and saying, oh yeah, this result is great for this query and this one isn't great. So let's try this out with our beer database. We'll just do the most difficult one that wasn't working quite so well with hybrid search after the first top result. So here you can see that the first result, and if actually we look at all the results, we get non-alcoholic beers for all the results. So the good thing about using a re-ranker is that it will also filter out all the results that you don't want. And in this case, the alcoholic results. And let's look at the pairing. So pairs with spice chicken pea wraps. So yeah, good pairing. Same thing for the second one. And you can see that these were actually good results for vector search. This one was ranked 3 using RF. Not so well using keyword search. And yeah, we still got our first top results from RF. But this time you can see that it's only ranked 3rd. So basically, yeah, the ranking, you can see some results moved down, some moved up, and all the ones that we didn't want were basically filtered out. So it's a really more reliable way to search for things. Let's look at what we did in there. So we did basically the hybrid search, but what we added at the end, we're using an LLM. In this case, I'm using GPT-5 Mini with basic prompt saying, okay, you're beer recommendation expert. Here's the user query, here's the list of candidates, and just give re-rank, reorder the beers to get the best result at the top. And yeah, that's how I got it. So you can still do that with LLM just as a way to, if you already have an LLM in your pipeline, that's a good way to get the quick results. Now you've seen an hybrid search flow on Azure Cosmos DB. And what's really exciting is that we can do native hybrid search today. The vector search, keyword search, and RRF are all natively supported. And even the final re-ranker step, I've just shown you that I'm currently using an LLM to do that, but it will soon be also natively supported. Currently, it's behind a private preview with SDK support for Python and .NET today. And we also have upcoming support for JavaScript and Java SDK. You can just sign up following the link in this slide if you want to get access, if you're interested into trying it. I'll just show you a quick glimpse of what it looks like. So as I can say, it's only available on Python and .NET for now, so I'm using the Python SDK. I'm using the exact same query and basically the same setup as before with the same request, except that this time for the re-ranking, I'm directly using the SDK re-ranker, and it's using a dedicated model, cross-encoder model to do that re-ranking step. So let's run it and have a quick look at the result. So yeah, results were a bit different, but quite similar in the end. We again have at the top result a non-alcoholic beer from India that matched with spiced chickpea. Again, just have a look. We all have non-alcoholic beer, so at least this was working just as what we had when we were tried with the LLMs. The good thing is that with a native re-ranker, the request will be faster and more reliable in the sense that the results will be more stable if you try to run the same request a few different times. So the reason that I'm talking about hybrid search today and why it's well integrated across all our Azure databases, including Cosmos DB, is that it really improves the relevance of the results. So this table is from research done by the Azure AI search team, comparing search strategies for different kind of queries. You can see that keyword search and vector search differ in kind of queries that they handle well, as we've seen in our example. But as long as we use a full hybrid flow with a re-ranking step, that we see great results all across all kind of queries. And we've seen in all how to implement a full hybrid search pipeline from scratch using Cosmos DB SDK. But to make it even easier, we also have worked to have a complete hybrid search integration in LangChain, both in JavaScript and Python. And I'm personally very interested in open source. I worked on this specific JavaScript integration, so really try it. I've been a long time LangChain.js contributor since the beginning of this library, and this is a framework that we really love here at Microsoft. Before wrapping this talk, I just want to show you what the final beer recommendation pipelines looks like for our burger agent. So we had our initial request for a spicy burger pick. I'll just ask, recommend me a good, let's say, what do you want? A good Belgium beer to go with it. And while it's thinking, let's have a quick look at how it's implemented. So this is our recommendation pipelines, so all implemented in LangChain.js. Currently, there's a slight limitation if you're doing keyword search, is that you can only use 5 keywords at most. So for our first step, we're basically using an LLM to extract the 5 most relevant keywords from a query if you have more than 5 keywords. Otherwise, we just take the query as it is. So this is a limitation that we have currently, but that will be gone in just a few months. I know the product team is working on that. Then we do the hybrid search with LangChain.js. So no complex stuff to set up. We can do it in one go, just pass it the query. We don't even have to compute the embedding ourselves. LangChain.js, once you tell it which embedding model that you want to use, it will do that part itself. It's all integrated. The number of results, the kind of search that you want. So we can try to redo all the demo ID just by switching the search type in there. And because this one will be vectorized, we still need to send in the keyword that we want to use for the full text search. And we get the results. And for now, because all I'm using is JavaScript in there, I'm using an LLM-based reranker, so the same one using GPT-5 Mini as I used in the previous demo. Once it will be available publicly in the JavaScript SDK, I will switch to that. And once I have like all my re-ranked results, I have just a final step to map that to the original entries that we had in the database, the JSON one, not the vector ones. And let's look at what it's look like in our like user agents. So yeah, with the spicy jalapeno burger, I wanted a Belgian beer, so at least I got 2 nice beers, and yeah, that's matched well with my burger. So this is how basically you can get some good beer to go with your burgers. So thanks for attending this session. You'll find here all the links and QR code for the burger demo application I've shown. You will have the full source code and related documentation also for Azure Cosmos DB hybrid search if you're interested into implementing that in your own application.